What if a black hole was created right here on Earth? This isn't science fiction. This is real science. Space is full of dangers, but few ideas terrify us more than a black hole. An object so extreme that once it begins to grow, almost nothing can stop it. So here's the real question: can human technology actually create a black hole? And if it can, are we playing with something we don't fully understand? In 2008, a machine was switched on beneath the surface of Europe, built to probe the deepest secrets of the universe. A machine powerful enough to recreate conditions just after the Big Bang. That machine belongs to CERN, and according to its own scientists, there is a non-zero chance it could create a black hole. Have we simply been lucky so far? Or is this fear wildly misunderstood? To find out, we need to look at the science behind CERN and the truth about artificial black holes. Do you think humans should ever experiment with something this powerful? We'll come back to this question later. In 2008, the global scientific community watched a moment that would soon become historic. Beneath the surface of Europe, CERN switched on the most powerful scientific machine ever built, the Large Hadron Collider. Its purpose was ambitious: to recreate on a microscopic scale the extreme conditions that existed in the earliest moments of the universe. But alongside that ambition came a statement that sent a chill through the public. According to CERN itself, the machine carried a non-zero chance, a probability that was not equal to zero, of creating a black hole. The reaction was immediate and intense. Some feared that Earth was being placed in a cosmic gamble. Lawsuits were filed in an attempt to stop the LHC from operating. Rumors spread rapidly, fueled by conspiracy theories and apocalyptic headlines. And in that moment, a fragile line emerged between rational science and humanity's deepest fears. At the center of every controversy stands a machine unlike anything humanity has ever constructed. The Large Hadron Collider, commonly known as the LHC, is not a single device, but a vast underground ring stretching 27 kilometers beneath the border between France and Switzerland. Hidden far below the surface, it is the largest and most powerful particle accelerator ever built on Earth. Inside this tunnel, beams of protons are guided by nearly 10,000 superconducting magnets. These particles are accelerated to 99.99991% of the speed of light, driven to energy levels so extreme they mirror conditions that existed only fractions of a second after the Big Bang. When they collide, it is not a simple impact, but a violent release of raw energy compressed into regions smaller than an atom itself. The scale is staggering. The LHC can generate billions of collisions every second, while consuming enough electrical power each year to supply a city of more than 100,000 people. This is not uncontrolled brute force, but carefully engineered precision, repeated relentlessly. What makes the LHC truly extraordinary is not just its size or power, but its purpose. Built and operated by CERN, it was designed to push physics beyond known boundaries, into realms where our current understanding of reality begins to fracture. So why, despite the fears and controversies, did humanity decide to build and operate the Large Hadron Collider? The answer lies in one of our oldest ambitions: to understand how the universe began. By smashing particles together at extreme energies, the Large Hadron Collider allows scientists to recreate, on a microscopic scale, the conditions that existed fractions of a second after the Big Bang. In that primordial state, energy and matter were not separate concepts. According to Einstein's famous equation E equals mc squared, energy can be converted into mass, giving rise to particles that did not exist before the collision. It was through this principle that experiments at CERN led to one of the most important discoveries in modern physics: the Higgs boson, the particle responsible for giving mass to other fundamental particles. Without the LHC, the Higgs might have remained nothing more than a theoretical prediction. But the collider's ambition goes far beyond a single discovery. It was built to confront the universe's deepest mysteries. What is dark matter? Where does dark energy come from? Why does matter dominate over antimatter? And are there deeper laws of nature hidden beneath the reality we observe? For scientists, the LHC is not just a machine. It is a gateway to the origins of existence itself. In nature, black holes do not appear suddenly or mysteriously in the way they are often portrayed in movies. They are born from extremely massive stars. When the nuclear fuel in their cores is finally exhausted, at that point, the fusion reactions that once pushed outward against gravity can no longer continue. Gravity wins, and the star begins to collapse inward under its own weight. When this collapse passes a critical threshold, matter is compressed so intensely that familiar structures can no longer exist. The result is a singularity, a region where density becomes almost infinite. Surrounding it is the event horizon, the boundary beyond which nothing, not even light, can escape. Crucially, there is no known law of physics that requires a black hole to be large. In principle, black holes can exist at many different scales. The defining factor is not size, but the degree of compression of mass and energy. In the universe, only the most violent stellar events produce forces strong enough to achieve this level of compression. And this is where the central misunderstanding arises. The real question is not whether black holes can be small, but whether it is possible to generate the required compression at all. That question lies at the heart of the debate surrounding modern particle physics and leads directly to the concerns surrounding CERN. To answer this question, we must talk about energy, specifically the energy involved in particle collisions. In particle physics, this energy is measured in tera-electron volts. While a single tera-electron volt may sound small, it represents an enormous amount of energy when concentrated into a particle as tiny as a proton. At present, the Large Hadron Collider can produce collisions with total energies of around 13 to 14 tera-electron volts. Future upgrades and even proposed successor projects may push this figure higher, potentially into the tens of tera-electron volts. But the crucial comparison lies elsewhere. To create a black hole according to our current understanding of physics, the required energy must approach the Planck energy, a scale at which classical physics breaks down and quantum gravitational effects become unavoidable. The problem is that the Planck energy is many orders of magnitude higher than anything the LHC can achieve, by trillions upon trillions of times. In other words, even though the LHC is the most powerful machine humanity has ever built, the gap between its collision energy and the energy needed to form a black hole remains vast. The provisional conclusion of modern physics is therefore clear. Within a four-dimensional space-time framework, the LHC simply does not have enough power to create a black hole. So, if the LHC isn't powerful enough, Why does CERN still say it's possible? And the answer may surprise you. If modern physics suggests that the LHC is not powerful enough, why does CERN still acknowledge that, in theory, creating a black hole is not impossible? The answer lies in a bold idea about the very structure of reality itself. We are familiar with a universe of 4 dimensions, 3 of space and 1 of time. But some advanced physical models propose that this may not be the full picture. Beyond the dimensions we experience, there may exist additional spatial dimensions, tightly curled up at scales far too small for us to observe directly. If these extra dimensions do exist, they would dramatically alter the mathematics of fundamental physics. In particular, the energy required to form a black hole could be significantly lower than the Planck energy predicted by a strictly 4-dimensional universe. Under such conditions, the high-energy collisions produced by the LHC could, in principle, reach the threshold needed to create microscopic black holes. These black holes would be unimaginably small and would exist for only fleeting moments. Yet, the possibility alone is scientifically profound. Detecting even a hint of such an event would provide indirect evidence that our universe is far more complex than it appears, and that hidden dimensions may truly exist. It is this uncertainty, not an imminent danger, that prevents CERN from ever declaring the idea impossible. But what if Hawking was wrong? Let's consider the worst-case scenario. Even in the most extreme scenario, where a microscopic black hole is actually created, this does not mean catastrophe. According to the theory proposed by Stephen Hawking, black holes do not simply consume everything forever. Instead, they emit an extremely weak form of radiation known as Hawking radiation. This process causes black holes to lose energy and gradually evaporate over time. Crucially, the smaller the black hole, the faster this evaporation occurs. For microscopic black holes, if they were to form inside a particle accelerator, their lifetimes would be extraordinarily short, lasting only tiny fractions of a second before disappearing completely. The amount of energy involved is also astonishingly small. Even under a worst-case assumption, the total energy released would be comparable to the motion of a tiny grain of sand, far too little to cause any measurable physical effect on its surroundings, let alone threaten the Earth. So far, CERN has found no evidence of microscopic black holes or Hawking radiation in its experiments. Nevertheless, highly sensitive detectors continue to monitor every collision in case such rare phenomena ever appear. In other words, even if the unthinkable were to happen, modern physics strongly suggests that our fear far outweighs the actual risk. Let us assume the worst imaginable case. Hawking radiation does not exist, and a microscopic black hole is created that does not evaporate. Even in this extreme scenario, the fear that it would swallow the Earth is not supported by physics. First, the gravitational pull of a microscopic black hole would be extraordinarily weak. Gravity depends on mass, and a black hole formed from particle collisions would have an almost unimaginably small mass. It would not behave like a cosmic vacuum cleaner, pulling everything around it inward as movies often suggest. In fact, outside its event horizon, a black hole behaves exactly like any other object with the same mass. And with such a tiny mass, its gravitational influence would be vastly weaker than other forces, especially electromagnetism, which dominates interactions at small scales. A useful comparison is the neutrino, a particle that barely interacts with matter at all. Every second, hundreds of trillions of neutrinos pass through your body without colliding with a single atom. In the worst-case scenario, a microscopic black hole would behave in much the same way. It would simply pass through matter without capturing it. As a result, the probability that such a black hole could continuously absorb matter, grow in mass, and become dangerous is effectively zero. Not because we are lucky, but because the universe does not operate according to the rules of science fiction. If this could really destroy the planet, why hasn't it already happened? There is one crucial fact often overlooked in debates about the Large Hadron Collider. The universe has been running these experiments long before humans ever existed. Every day, Earth is constantly bombarded by high-energy cosmic rays. Particles accelerated naturally by supernovae, black holes, and extreme events far beyond our galaxy. When these particles strike Earth's atmosphere, they collide with other particles at energy levels equal to, and often far greater than, anything produced in a laboratory on Earth. If collisions of this kind were truly capable of creating dangerous black holes, then such events would have already occurred billions of years ago, not only on Earth, but on countless planets throughout the universe. Yet there is no evidence that these natural collisions have ever triggered planetary destruction. From this perspective, CERN is not doing anything uniquely hazardous. Its experiments simply recreate, under carefully controlled and continuously monitored conditions, processes that the universe itself has carried out naturally for eons. Seen this way, the fear that CERN is gambling with the fate of the planet collapses under its own weight. The cosmos has already tested these limits again and again, and Earth is still here. When we step back and look at the full picture, one thing becomes clear. For an experiment at CERN to trigger a cosmic catastrophe, a chain of extreme and unlikely conditions would all have to be true at the same time. The probability of that happening is effectively zero. Science does not advance through blind recklessness. Every step forward is tested, challenged, and carefully monitored. The Large Hadron Collider is not a doomsday machine, but a precision instrument built to help us understand the origin of matter, space-time, and our place in a vast and complex universe. Perhaps the most unsettling thing is not black holes themselves, but how much remains unknown. And it is curiosity, balanced by humility, that has always driven human knowledge forward. If questions like this keep you curious about the universe, consider subscribing. There's a lot more out there, and we're just getting started.